Okay. For dispersive media, we have these Maxwell's equations, including D field. So the updated equation is modified to okay. So now the so the updated equations are 3 and 4. So let's see what happens if we update the field. So I'll show you the leapfrog process. So when n is equal to 0, then you have E field 0 and D field 0. Let's say initially there was no field at all. And then n equals half, you have also initial H field 0, and but J is given. So you jump to n equals 1 point using using 4. Yes. And then by using the updated equation 4, what you get is D at 1, right? And you want to use D at n equals 1 to update H field. But here you don't have E field. You don't know the E field at this point. So you updated the D field, but you haven't updated the E field, right? You don't know the E field at the same time step. So as a result, you cannot update H field at this point. So we should recover so once you update the D field, you have to recover the E field from the updated D field. And by discretizing the D and E field relationship, what you get is this. So this is just Riemann integral of the integral. I mean the Riemann sum of the integral. Right? So for small delta t, you can approximate the D and E field relationship accurately using this sum. And then this is so I simply took m equals n term out of the summation. I'm sorry, m equals n plus 1 term out of the summation. Then what you get is the expression for E at n equals n plus 1. Okay, so this is equation 5. So if you include this equation 5 to the previous updated equations, you get a set of updated equations for dispersed media. So on the right hand side of this new updated equation, you have updated D field you get from equation 4, and you have to use all the E field from n equals 0 to the previous time step. So you already know this information. So you can actually update E at a new time step using this. So, however, the new updated equation 5 requires the entire history of the E field. Which is very storage intensive. So to use this updated equation, it means that you have to store the E field in entire space through the whole time. For 3D simulation, this is very costly. Usually, for non-dispersive media, you just update the E field and discard the old values. And if you want, you can store the snapshot of the E field at a given time. But usually, you don't store the entire history in entire space. But to use this updated equation, you have to store the entire history of the E field, which is very storage intensive. So actually, there are better algorithms there are stories efficient. So there's a storage efficient variant of the equation 5, which is called a recursive convolution method. So the reason why it is called recursive convolution method is that the equation 5 is basically a convolution equation, right? So equation 5 is this convolution equation. So there's implement this convolution by introducing extra variable, and you can use this extra variable to evaluate a convolution recursively without storing the entire history. So yeah, but what I'm saying is that in principle, by looking at this simple argument, you know that you can handle dispersive media in FDTD. And if you're actually interested, then you can look for this recursive convolution method. I think I have run out of time, so I'll stop here. And maybe next time I can spend like 15 minutes to finish up.
Yeah, just a couple of announcements quickly. First, thanks to Wonseok for this last week of lecture. We have an additional lecture specifically on scattering in FDTD and with numerical. So, so you'll be back. Yeah, don't throw eggs at him just yet. The second thing is, and next week we will be starting topics on extinction, scattering, and absorption, and Dan Parker scatters, starting with the definition of what extinction and scattering are, and then going on to mean theory. So we've basically finished one module of Green's functions and dipole interactions in the near field, and we'll be going on to actual scattering of particles, and then looking at their behavior in the subwavelength limit, what happens if the particles are metallic, so on and so forth. The second thing is there are some questions about homework 3 on what is expected. We'll update homework 3 on the website, but in terms of saying a few words about your project with your partner, I'm thinking of 2 paragraphs.
Homework 2.
Or sorry, homework 2?
Yeah.
Problem 3.
Should edit that video. Homework 2. So problem 3 is to discuss your project. I'm looking not for like something huge and extensive, but something on the order of 2 paragraphs. One with a little more detail on what what your topic is about, and 1 paragraph about what you propose as your actual analytic or numeric computation project, followed with a couple of resources. You know, they can be ones that were sent out. Hopefully they include slightly more detailed ones on specific topics. For example, if it's photodetectors, what specifically are you going to be looking at? So I just want to make sure that everyone gets together with their partner and hashes out kind of the project and in a little more detail. But this is not, you're not supposed to do the project now, right? I mean, this is over the course of the entire lecture. And I think that's it. And just one more thing, for Friday, there will be a recitation for anyone who has questions about numerical, both in terms of installing it. I think Sunghyun has sent out an email with instructions on how to access the license server, but in case you have any questions about that, and in terms of general use of setting up simulations, I know there are videos on the tutorial website, but sometimes it's useful to see it in person as well, and to ask questions in real time. So Sunghyun has some experience having used numerical, and so that will be tomorrow. All right, I think that's it, and we'll see you.